I'm audible, ma? Hello?
Yes, sir.
Hello? Okay, ma. Okay, we'll see some numerical problems. So, and then we'll compare the genetic algorithm and conventional algorithms. And after that, there is a one test function. We'll take it and we'll solve the total complete problem. It is a last topic of this unit that we'll see tomorrow or day after tomorrow. We have only 2 more classes required for this to complete this unit. Then after that, I will share this document. Now you can see the normal function. Let it be in the problem, maybe minimization problem or a maximization problem. Anything we can do. Some examples I will explain the maximization problems. After that, I will consider one problem step by step manner how to solve complete problem for minimization problem as well. Because in all our power system problems, we are able to do objective function maximum cases as a minimization or anything. It is not a different. If it is minimization, we will take as a minimum solution is a best solution, or maximization means maximum solution is the best solution, like that. Now, example one, I've taken f of x is equal to x square. This is our function. Now, how to solve this function? Some more data also they have given. You can see the function is considered f of x is equal to x square is the function, and in that they have mentioned minimum value and maximum value of that function. Minimum value is 0 and maximum value is 31. Now we'll see the encoding technique. As you are aware that to get 31, we required as a some minimum bits. That is minimum 5 bits are required, because 0 means all 5 bits you can make it to 0. And because it is a binary coded encoding, later point I will explain the real coded also one of the problem, so that we can understand the difference as well. Instead of binary coded genetic algorithm, if you go for real coded, it will be simple further. Instead of all taking these binary bits, all this thing, there we don't require to take binary bits and all, directly values you can take it in the case of real coded genetic algorithm. Now we can observe maximum value is something 31. Then if it is a maximum value is 31, we can observe that this will be 2 power 0 and 2 power 1 and 2 power 2. Like that, we need to take all 5 bits we can consider. In that case, if it is a 31 is a maximum value, then we can go for as a 5 bits problem. Then only it will get it as a 31. So the function is given is to be next, select the initial population as per our steps. We need to select the initial population. To start that problem, initial population we taken as a randomly. How many populations you want, you can define. Let it be for simplicity. I have taken as a 4 populations. Now, 4 populations, suppose 1, 2, 3, 4 populations are population we are taken as a 5 bit. Let it be some numbers, 5 numbers, 0, 1, 0, 1, like that. Any numbers you can take it. Whatever you want, you can make use of, because it is all random only. Like this, we need to take it. That is only the first step. Select the initial population. While selecting the initial population, what we want is we need to select randomly, and after that, the how many populations you want, do you decide that? Let it be as a four I have taken, and that we can see in the table data. What we have taken is a four populations I have taken. This data is random data. Because why I have taken 5 bits? The problem, they may not be mentioned. The number of bits depends on our requirement. Whenever we require to generate a random bits, that how many bits you want to select, that is based on the what you call it as maximum value. Let we can consider maximum value in our case 31. So we cannot take it as a 4 bits. If I take 4 bits, what will happen? 2 power 0, 2 power 1, 2 power 2, 2 power 3. What we can get? 2 power 0 is 1. This is 2, 4, 8. So if I add all these things, if I give all ones in that bits, how much you can get? 8 plus 2, 10, 14 total only I can get the 15 maximum. But in our problem is mentioned as a 31 is the maximum. That is the reason we have to go for as a 4-bit problem. In that case, we can add um, 16 here. So then the total will be as a 31. So that is the case. We need to select as a number of bits. So now we got random generation like this. Now we have to convert this random bits chromosome to real value. Now we are encoding. So how can I get the real value? Here it is very simple. I already explained in the introduction class itself. Whenever binaries are there, you can just multiply into this bit value into 2 power 0, 2 power 1, like that we have no. So 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. Now wherever 1 is there, let it be 0 into 2 power 4, that will be 0. And then 1 into 2 cube, 8. Then again 1 is there, 1 into 2 square, 4, and rest will be 0. So 8 plus 4, that will be as a 12. Similarly, we can see here there is a 1 that will be first bit, I mean this side 2 power 4, so that is 16, and plus next bit also 1, that will be as 8, and others are zeros, and last one will be 1 into 2 power 0, that is 1. So now how many we got it? 9, then 25. If I add all these things, we'll get it as a 25. Similar fashion, we need to find out for all the bits what is the x value. So in this case, 1 into 2 power 0 plus 0 into 2 power 1, then 1 into 2 power 2. This will be 4 plus 1. So that will be as a 5. Like that, you can calculate the real value. So x value is this one. Once if we know x value, we can easily find the fitness. So in this case, fitness value and function value are taken as same. No, 12 is the x value and our fitness f of x is equal to x square. This will be as a 12 square. So this is nothing but a 12 square. And another one is 25. This will be as a 25 square, and then 5 square, 19 square. So like that we'll get it as a fitness value. Now we got all the fitness value. After that, probability to go for next level, there is a formula here. Probability is f of x by summation of f of x. So you just sum all the 4 witnesses. We got 1155 is a summation. So now f of x is a 144 divided by 1155. That will be as the probability. Now how much you can get it? Same value, 144 divided by 1155. So that will be as a probability 0.1247. Similarly, 625 divided by sum is 1155. So that will be as a 0.5411, 5411. Like that, we'll get the probability. Then percentage, just multiply by 100, and these are the percentages. Now, expected count. So here we can see for that we have is another formula. What is the expected count? So whether it is a one time it will be repeating or two time it will be repeating, all these things that will be getting as a expected count. In that case, there is a formula f of xi divided by average of sum. Now we already calculated the this value is a average of sum. So sum is 1155, then average is 288.75. Therefore, this value will be obtained. The formula f of I is first population, let it be f of xi is 144 divided by average is 288.75. That will be as a 0.4987. Like that, you can calculate next one. What is the next one? 625 divided by 288.75. And similarly, you can calculate all other expected count. Once if you get the expected count, then actual count you can see. You just round off. You can see expected count is 0.49. Then you make it as a 1. Because it is nearly 0.5, so just round off to 1. And 2.16, then that will be make it as a 1. I mean 2. So 0.0, so this will be as a 0. 1.25, make it as a 1. So now what is happening in this? Actual count is here is 2, here is, I mean, here is 1, 2, 0, then 1. In that, how many populations we need? 4 populations. So what is happening? 0 means this random data or this chromosome will not go for next iteration. So our next course of evaluation. So what will happen? You simply discard this. Then we'll go for as a next procedure. What we can do is 4 we need. No, here 2 is the actual count. So you repeat, this will be 2 times. This will be 1 time. And this will be 1 time. Again, we'll get it as a all 4 chromosomes. So now we can see that's what I mentioned here. The actual count is 1 means only 1 time in the mating pool, and 2 means 2 time in the mating pool. We need to go for as normally. I will show in the next example. So the last example, it is only to understand small example I have taken, and there I will take a bit more procedure orientation so that the real problem we can solve it. In that case, normally mating pool, we can go for as a tournament selection also, we can use it. Just two, we can select which one is having as a more fitness, that will be selected for the mating pool. Like that also we can do it. That we can observe later point of time. Now we can see crossover operation. So whatever we have so far, just random selection, after that fitness calculation. Once if we complete these 2 steps, the third step is a crossover. Next step is a mutation. And then we'll go for as a repetition of this loop. Then finally termination process. So this is what we can able to do our problem. Now what is doing is calculating the fitness is completed. then we'll go for as a crossover. How to do the crossover? First, we have to select the mating pool. How can I select the mating pool? As per the previous, you can see from this I have to select as a mating pool. In that 0 is there. I will not take this in the next for crossover purpose. I can take first one because it is one time, and second one two times you can take it. Third one you don't take, and fourth one you make it to one time. So like that, we can easily do this process. Now, so I will take this one first in mating pool 0 1 1 0 0. Then this you can take it two times. 1 1 0 0 1 two times you can take it. This will be one time. That's what I mentioned here. So now this is the first one. The second one will be two times. Third one. Now how to do this in the crossover? So crossover, different types of crossovers I explained in the previous class. What I can do is just select two parents and perform the crossover operation. So here totally what we can get it four offsprings will get. First two parents perform the crossover, two offsprings will get. The next two parents perform the crossover, another what you call it as just a minute. This will be this will not be here. That will be here. To this. Yeah, no. Now what I'm doing, so first this one, yeah, just a minute. Yeah, so first two parents I have taken. This is the because mating pool we have four, no? First two parents you will take. So for parent one, 0 1 1 0 0. This is the parent one, and parent two, I will take this one 1 1 0 0 1. Now what I'm doing is randomly I have to perform the crossover point, whether it is a 2 or 4 or 3 or anything, you can select randomly. Just for selected as a 4 is a crossover point. Then I draw as a line. Then we'll get as a two half springs. After the crossover set, that will be 4. I selected. It is all random. There is no meaning to select only 4 or 2 or 3 or something. Just crossover points I taken. First thing 4. That means you draw a line 4, and after that you change the bits. That's what I mentioned. Offspring 1 and offspring 2. Up to this will be remains. Then this 0 will come to here and 1 will go to here. So that's what offspring 1 and offspring 2. Similarly, you take these two parents, that is parent 1 and parent 2, these two, and I taken as a crossover point is 2. That's what I mentioned. Crossover point is not fixed one. That will be as a sometime 3 or 2 or 1 or 4 or 5, anything you can take it. Some cases you can notice the after before the line they may be change that parameters. That also you can do it based on the fitness function. We can able to observe whether it will take more number of iterations or less number of iterations and all. Now what is happening is here we can observe the second one is a crossover point is 2. I taken 2 is a crossover and these bits will be swapped. That will be offspring 1 and offspring 2 for this. Now if you want to can name differently 1 2 parent, then 3 4 parent, and offspring 3 offspring 4 also you can use it. Now we got the offsprings that you can write it here. So you can see this will be the first offspring, then this will be as a second offspring, then third one, and then this will be as a fourth one. Now we got all the offsprings, all four offsprings. After that, x value. As usual now, how can I get the x value? You convert this binary to encoded value. 1 into 2 power 0, 0 into 2 power 1, 1 into 2 power 2, like this. Just I will show you this one. 1 into 2 power 0 plus 0, and then 1 into 2 power 2 plus 1 into 2 cube plus 0. So this will be 13. Like that, another offspring 2, that will get it 24. Then offspring second list of parents will get 27 and 17. So what we can do now, we have x values substituted into function that will be as a fitness. So now again, you can simply substitute this 13 square, 24 square, 27 square, 17 square, like that. Now what is the sum here? What is our intention is we have to find the maximum function value. In the previous, we noticed the function value, maximum function value is 625. Then we performed the crossover, we got it as a 729. It is a improved cross after crossover. Now we not completed this problem. What is the next step we have? After crossover, we will go for as a mutation also. And we can notice after mutation, what is your function value also. Like that, the problem will repeat continuously. You will get it as a final stopping criteria. Once the stopping criteria is reached, then you can stop the problem like that. Now we'll go for as a mutation. So what mutation will do? Again, offspring, whatever we have taken in this, these things we can take, because after crossover, we got 1 0 double 1 0 1 double 1 3 zeros, like that. All we have taken as a offsprings. Now then we'll go for as a mutation. Again we have as a more number of methods in a mutation. The flipped or bit swapping or anything you can take it. What I will do is randomly I select the these four chromosomes. In that, wherever one is there, that bit will be swapped. That's it. That is only one of the mutations. Now I can, for example, I have taken after of crossover. This is the bit. I mean chromosome I have taken. What is that chromosome? 0 1 1 0 1. So this is the chromosome. Now, correspondingly, I have generated one random chromosome for flipping. So, in the random chromosome, wherever that is like a task, you just make a task. Wherever head is there, that will be 1, and tail is there, we will make it to 0. And then you're going to do the mutation. Wherever ones are there, you can do that. So, in that case, after crossover, we can 0, 1, 1, 0, 1. That is the case of offspring. Now, you can do the mutation by taking as a random chromosome. Now, in that case, 1, 0, 0, 0, 0. So, only first bit will be as a 1. So, now corresponding bit, if the corresponding already existing 0, make it to 1, or existing bit is 1, you make it to 0. Like that, this bit is going to be changed. That's what I did here. Now you can carefully observe one small, this will be as such, you can write this, you can write as such here. And now in the mutation for flipping case, this is the toss I did, and wherever one is there, there the flipping is going to be takes place or changing. Now in this position 1, already bit is 0. That's the reason I make it as a 1. Remainings will be as such, because all remainings are zeros only. So wherever 1 is there, you can flip that. Now suppose already in this 1 is available. Now the lower part is again same. Now what I will do in our mutation, after mutation, this 1 is replaced with 0 because this task is head, you can do the mutation. Because in this case already 0 is there, I make it to 1. Suppose existing 1, now you make it to 0 here. Like that, you can do the mutation. That you can, not only this method, any method you can follow to do the mutation. In that case, I did mutation for this. What is happening? All are tile. That's why we are not changed any thing. This will be exactly same as this. But now you can see this also all are zeros. So this will be remain same. Now we can observe the last one, fourth chromosome. Existing is this one, and then random chromosome is this one, and wherever one is there, that bit is replaced here. How to replace? In that one position, the existing is 0 means make it to 1, or existing 1 means make it to 0. Now we can observe the last bit, mean this one in this side 2 power 0 position head. So 1 is there. That's why here existing is 1, I make it to 0. So that's what I make it to 0. And third bit, this one, it is 1. And here third bit is 0. So I make it to 1. So like that, I can able to do the offspring. So X value I can perform 2 power 0, 2 power 1 and so on. The count will be as a 20 because this is your final after mutation. Now we got after mutation the X values. Then you go for as a fitness. Now we can observe the maximum value is 241. You can compare line by line here. Initial calculation, random population, we got 625. Then we performed the crossover, we got 729. Then performed the mutation, we got 841. So like that, keep on increasing this, and all the steps are over. Then what we can do is repeat this problem for next iteration. So now we got this is your after mutation. These are the what you call it as offsprings. Now we do this for next iteration. Then you can do the crossover, then do the mutation, again go for next iteration like that. Whatever the set values we are going to do, whether it is a 4 times or 6 times like that, we can easily go for the stopping criteria after 10 iterations or 50 iterations. In the real problem, you can take it as a number of populations itself as a 50 and go for 100 iterations and then for print the result. That is the procedure. Next you can see only different is function. Earlier problem 1, f of x is equal to x square. Now the function is something different. F of x is equal to minus x square plus 2x. Now with this you can solve the problem. So here different version also I mentioned here. What is the maximize the value of function f of x is equal to minus x square plus 2x over the range of real number from 0 to 2 with initial population. Now the initial populations are given in a problem. In sometimes if initial populations are not given, what we can do is initial population is not given, then you can generate your initial population. But in this case, they have given already. And random numbers also given with random number 0 0.4, 0.15, 0.7, 0.99 like that. Select the crossover between first and fifth digits. Now the two parents will take it and you take it as a first bit and fifth bit in between. You can change the exchange the bits. This is what the crossover also is mentioned. If this data is not mentioned, You can take, I have taken in the previous problem, like fourth bit and then second bit, like that. In this case, is a 2-bit crossover. First and fifth we can take. That way also can take it, or maybe first parent, first two parent, one parent two, we perform the crossover at the first bit, and then parent three, parent four, we can perform the fifth digit also, like that, or 2-point crossover. Now you can see the problem. Minimum value is 0, maximum value is 2. That also is given. As per the problem definition, initial chromosomes, you can take it directly from the given problem and select the initial population, means individual, 4 individuals only they have given, because size is mentioned 4, population size is 4. So therefore, you can take the individuals are 4. Then what we can do is decode the individual into a real number. So this is the formula: minimum plus maximum minus minimum by 2 power n minus 1. So into this value. So these are all we can easily convert into. So this will be as a 26, this will be as a 7, this will be 22, and this will be as a 5. So this value you can go for as a decoded value also, because directly you can do this. We are going for multiplication of this, we can do it later point of time also, or just make it as x value here. Because this, suppose if I take this 0 into 2 power 0, 1 into 2 power 1, then 0 into 2 power 2, then 1 into 2 cube, then 1 into 2 power 4. So if I do this, I will get as a 26. After that, you can go for as a decoded individuals also. So now same thing, we can make use of this fitness. This is a function, or similar manner also you can do. You convert into here values, and here fitness value, that real value you can substitute it, and probability and cumulative probability, that procedure. This is a bit different way we can see here. What I did is decoded individuals using this formula, and after getting this, this is the decoded value. And probability, now we know the formula f of x by summation of f of x, that will be probability. And cumulative, how we can get the cumulative? Simply 0.21 plus 0.27, that will be 0.48, and 0.48 plus 0.32, that will be 0.8, 0.8 plus 0.2, that will be as a 1. Now after getting this 0.21, that is random number between 0 to 0.21, and 48 means 0.222, 0.48. Then this 0.8 means 0.492, 0.8, like that. And there is a range we created here. And then next step, we can see these random numbers are already mentioned in a problem, 0.4, 0.15, 0.7, 0.9. Then you know, because this is given in a problem, now we already calculated what is the range between that. Suppose they have mentioned here, the problem is 0.4 is given in problem. 0.4, in which range? This is the range. That means 0.22 to 0.48 range. That's what I mentioned here. And 0.15 is related to which range? 0.15. This is the range. Then I can write that one. And point 0.7, that will be belongs to this range. Like that, you can decide the range here. In that range, choose the string. Now, in this range, what is the string? It is already available in the problem, 0.22 to 0.48. 222.48 is string is this one. And another one, you can see this 0.15 is string is what? 0 to 21, first string. You can take it, this is the string. Like that, you can choose the string. Then now we'll go for as a crossover. What in the problem they mention within each pair of swap part of the number solution to create offspring which are mixture of parent. What is the parent they have taken? These two are the parent because first two parents do the crossover, we'll get two offsprings, and then these two can get the another two offspring. Now choose the two strings at that point, that is a 0 0 1 1 1 1 0 1 0. These are the two parents. Now, as per the problem is mentioned, you can take it as a crossover points. First and fifth digits you can take it. Or if it is not mentioned in problem, you can take it your own method. Crossover methods, we have different crossover methods. You can take it any one of the crossover method. Now, here is a first bit and this one is a fifth bit. And then we can able to get it this yield. Now, what we can do is first bit, then fifth bit I have taken. So between bits, you are going to exchange in the offspring one and offspring two. So this is a parent one, parent two. Then first bit and fifth bit, you draw the line. These two will go to up, these two will come down. So this is the uh, after crossover. Similarly, you can do next two. Next two I taken, and here also first bit and fifth bit you taken. 0 1 1 will come down and 0 1 0 will go up. These are the two offsprings. This is the offspring one and offspring two. Once we are getting all the four chromosomes or offsprings after crossover, you need to do same procedure. Now this one after crossover. Again you convert into individual encoding, and this is 11, this one value 22, 27, and then you convert into encoding value and put it into function. So now what is happening? Maximum function value is 0.915. Earlier, what is maximum function value? 0.824. So like that, now what you can do, you can go for as a probability. Probability is nothing but a f of x divided by sum of f of x. Then cumulative, then interval. So range. Like that, you can repeat this problem continuously, then go for as again mutation, then crossover, again mutation, crossover, like that. If you do that problem, that is the second way of solving a function. Then third one you can see, again maximization only. If I take f of x is equal to x cube, that is your function. So now you have to solve the problem. Again, if any data is given in a problem, we can make use of that data, and then we got to proceed. So here the function range is given 0 to 15. So 15 means, I don't think so we required as a, but it is not mandatory to take this many bits, but preferably even 4 bits also is sufficient, because 4 bit maximum, how much will get? 2 power 0, 2 power 1, 2 power 2, 2 power 3. So this is 1, then plus 2 plus 4 plus 8, then 12 plus 3, that will be as a 15. So therefore 15 up to 4 bits also sufficient, but in problem if they asked more bits, then also you can choose the chromosomes will be like that. Then applications first step is decide the chromosome. A binary encoded and in that 0 to 15, so therefore 4 bit is sufficient. Then we have to select as a random sequence. So first iteration randomly you have to choose, but if it is not mentioned random chromosomes, you have to take it as a random chromosome. No, for that only 4 bit I have taken. Same example of one. First example and this example exactly same. Second example bit different. Now once if you get the chromosomes randomly like this, then you have to get the real value. So 2 power 0, 0 into 2 power 0, 1 into 2 power 1, that will be 2. This will be 4 and put it into function. Then go for as a probability. This is the probability, and this way also you can do it after percentage. Then there is a, you can see in the first problem, you can easily understand this one. Yeah. So percentage, what we can do is expected count. We can get it as expected count directly using f of x by, because whether you can do this or in that third problem what they did is after fitness directly use it as expected count, that way also, or you can do it probability then go for as a expected count. Now we can see here expected count that will be f of x by average of summation of f of x. So we have average value also, and f of x is equal to 8 divided by 886.25 and 64 divided by 886.24, like that if we do, we'll get it as a expected count. In that 0.00 will make it as a 0, 0.07 will make it as a 0, 0.8 will make it as a 1, 3.09 make it as 3. So from this meeting pool, what is mating pool? These two we have to discard. This you can discard, this you can discard. Then I need again 4 chromosomes. This will be once, this will be 3 times. You can take it. So now what I can do, 1, 0, 0, 1, you can take it only once. And here is a 1110, that you can take it as a 3 times, because mm, truncated to nearest value we will get this 3 times. So mating pole will get 3 times, and first one this will get only 1 time. In that case we can easily observe that crossover point randomly chosen, this are the 3 times and this will be as a 1 time. And now crossover point, where to do the crossover? Two parents you can take it and do the crossover at 3. And this two you can take it, do the crossover at 3. So in that case, we'll get as a offsprings. So now to show you these two parents, because these values are same, 1, 1, 1, 0. Crossover point is 3. So this two will exchange again. That will be remains offspring 1, offspring 2 will be same. But whereas if I take these two parents, 1, 1, 1, 0, another parent 1, 0, 0, 1. The crossover point is 3. This is our crossover point. Then what is offspring 1 and offspring 2? This 1 will go to up, 0 will come down. Then your offspring 1, 1, 1, 1, and lower side 1, 0, 0, 0. These are the offsprings. So that's what I mentioned here. So now we got the offsprings, and we got the upper side two offsprings, lower side two offspring, totally 4. Now we'll perform the same for the rest of the things. So you can go for as a after crossover. Now we got this, then we'll get the function value. Now what is maximum? This one. Earlier What is maximum? 2749. Now after crossover we got this. Again we'll do this count, rounding that. And this is the expected count. We got 1.17, 1.17, 1.4. This will be make it to 0. So this through 1 will be getting. And now what we can do is, so you can repeat this problem for mutation and then crossover, mutation and crossover, like that number of iterations fashion. And similarly we can see another concept, genetic algorithm versus conventional optimization techniques. This is also important. We noticed that the conventional methods as well as the genetic algorithm, we can observe that such space for problems refer to compiling all potential solutions are that problem, whereas the traditional algorithm only maintain single set in such space. So there is a multi-agent, so the total search space are dividing into parts and each agent will search the results and will combine together. But whereas in traditional algorithm, only maintain a single set in the search space. In contrast to the genetic algorithm, which use several sets in simultaneously. In GA, we'll get it as a several set simultaneously, but in traditional only one set is going to perform. To execute searching, traditional algorithm requires several parameters, whereas GA just requires single object to function. Another one, in GA, to evaluate the fitness of organism more accurately, whereas in the serial number of traditional algorithms, GA can run in parallel, as I mentioned, and this traditional are only capable of producing single optimal solution. Traditional can capable to produce only a single optimal solution, but several generations of GA may provide a large number of optimal answers. Now, can't there is to popular option, traditional algorithms are not better prepared to identify global optimal solution, whereas genetic operators such as crossover and mutation improves the possibility of discover the such solution. Because of this, what you call it as crossover and mutation operations will do the possibility of discovering such solutions. Then there is not guarantee to discover such solution in the other cases. This genetic algorithm probabilistic and stochastic, whereas traditional algorithms are deterministic. So here is a random that we call it as stochastic, means it is a random population, but whereas in traditional it has to be deterministic. And the predictional algorithm, that is traditional algorithms, have difficulty deadline with multi-model real-world problems, and still genetic algorithms, when give the appropriate parameter setting, can handle these problems quite effectively due to the large amount of space developed in the potential solutions. And some more parameters comparisons you can see in the definition wise: usage, complexity, applications, working, search area, info, rules, like this. So we can see genetic algorithm for solving both constrained and unconstrained problems, optimization problems based on genetics and natural selection, whereas traditional algorithm unambiguous specifications we required to solve. Usage case, you can see that helps to find the optimal, near optimal solution for the difficult problems. Provides the step-by-step methodology. There is a methodology procedure to solve a problem. Complexity, advanced. Here is a genetic algorithm will be as a more advanced than traditional, and you can see the applications, lot more applications, fields such as research, machine learning, artificial intelligence. In that area, we can use this genetic algorithm. Programming and mathematics area, we can use traditional thing, and coding of parameter, and the parameter is can use directly, and such space population of points, and here is only the single point. Like that we can get the some more comparison. Like this here also I mentioned some comparison. And another way in the what you call it as in the conventional and genetic flowchart wise, we can observe that initial single point will be there in the conventional, whereas here the population will take it as a initial population. So that may be any n number of populations. Here n may be 4 or n may be 5, or based on the problem you can take it as a 50 populations like that. And then improvement problem specific, but whereas here problem independent, that is keep on improving. We have a lot of operations inside. One is a crossover operation, another one is a mutation operation, like that. We are doing as a continuously. Then we'll go for as a termination process, and if it reaches to the termination, then we'll stop it. Otherwise it is keep on repeating that. These are the some of the. And another, what I mentioned in the theory part, that I'll make it in terms of the comparison wise. You can see the single point search in the traditional case, in the whereas in the GA and evolutionary case, population base. This is a gradient search. This will be as a random search. If this is a deterministic, and it is algorithm will be as a random parameter, stochastic, and mathematical operators, and this will be random genetic evaluation. Fast but required gradient information will not run for non-convex or discontinuous problems, and some solution every time, but the solution depends on initial guess, and different solution in every run, but little effort improvement will be there from the initial population. Like that, different solutions require for different functions, but independent of the objective function, we can proceed. So these are the comparisons of genetic algorithm and conventional, and we'll see in the next class. There is a different small topics will be there. I will close that, and after that we'll move on to one example and how to solve the genetic algorithm. If you have any doubt, you can ask me.